Okay, so what did we learn in the last lecture? I thought I changed this already. Why it becomes this again? Okay. So in the last lecture, we talked about the transistor. We talked about the linear mode and the saturation mode, right? You remember when it is in the linear mode? Just a quick review. We know the current is going to be W on L mu COS times VGS minus VT, the whole thing times VDS, right? Minus VDS squared divided by 2. Particularly is that when the VDS is very small, right? When VDS is small, it behaves just like a resistor. Right? And then it's talking about this region, right? This region, it is all very straight. It is linear. It looks like a resistor. But then when the VDS increases, right? For large, and when do we have the linear mode? Do you remember under what situation? Less or large? We're talking about small VDS, right? So do you want it to be less or large? There's a way to memorize. Right? We say that when the VDS is small, then it's a resistor. Then probably you think VDS must be small, right? So it means that you want the VDS minus VTH to be, VGS minus VTH to be larger, right? Because when it's small, then I will be larger than you, right? So that is a way to memorize, right? To help you memorize. And this is the linear region. And we also call it trial region. Or it works like a resistor. But if we keep increasing the VDS, eventually when VDS is larger or equal to VGS minus VT, it enters into the saturation region, right? And this is the region at which you can use it as a current source. Why it is a current source? Because it has a constant current regardless of the terminal voltage. Right? What is a voltage source? No matter how much current it delivers, it has this constant voltage, right? When you buy an AA battery, you hope that it always gives you 1.5 volts, whether you use it to power your clock or power whatever gadget you have. They draw different amount of current, but they still give you 1.5 volts. And what is a current source? It's the same. Whether you apply 1 volt across it, 2 volt across it, you hope that it always give you 1 milliampere. They have this type of duality, right? So if sometimes when you deal with currents, you don't understand it, think about in the voltage domain. Okay? But anyway, the point is that, then when you go to saturation, I have this current, right? And I know this current is constant. And however, in reality, it still depends on the VDS a little bit, right? That's why I have this line, which is called channel length modulation, right? This is CLM. The reason of this is because the pinch off location keep moving into the channel. So effectively, that resistor is shorter for the same condition. That's why the current will go up. Okay? I hope that you agree with me. But we can look at PMOS again, and that can help us to review, right? So what is PMOS? It's P-type. Everything is the same as NMOS, except that this time we have a lot of hole in the source and drain, and in the substrate we have the electrons because it is the N-type. Everything just opposite. Change the polarity. So let's look at the scenario, right? For example, this is P plus, this is P plus, and this is N. In the NMOS, we say that if the gate is very high, very low, I'm going to attract a lot of hole, right? So in PMOS, you are going to have the high VG, maybe VG equals to 5 volts, for example. What will happen when you have a very positive voltage at the gate? You will attract the electron, right? Because it's going to attract the negative charge. I start with positive voltage, right? In NMOS, I start with negative because I want to attract the hole. Now I am going to attract electron. Yeah? So does it conduct any current? I basically have the same scenario. It's still a back-to-back PN diode, although in the opposite direction, right? We call this accumulation mode. Same. I'm accumulating the electron to the surface. Just like in the NMOS case, I'm accumulating the hole to the surface, right? Because now the substrate is N-type, not P-type. And if I start reducing the gate voltage to, for example, negative 0.4 volts, okay, I assume the VTH is negative 0.7 volt, for example. Then what will happen? I get more and more negative, right? The substrate is N and you get more and more negative. Then I'm going to repel the electron, right? So here I will have a lot long-mobile ion here, which is positive. Again, just like the analogy, I have a tube, I have water on the two terminal, but at the middle is all ice. This is a frozen water molecule, right? Long-mobile, immobile positive charge. So I still don't have current, right? But this is like the NMOS case. Now it is in depletion because it expelled all the electron and you still did not induce any hole. It's depleted of carrier. Okay? Eventually, I have a very negative bias, let's say negative 1 volt. Using the same analogy or same discussion like we did before, yeah, I do have some depletion charge, but this time I start accumulating some hole here, right? Because you're negative, I attract a lot of hole, right? So this is in the inversion regime, right? Because the substrate was N-type. Now I induce a lot of hole. It becomes like P-type at the top. That's why I inverted the channel. So now I have current. So everything is the same, except we need to recognize that the substrate and also the carrier is changed. And then as a result, the potential need to be flipped over from the positive world become negative world, right? So in NMOS, when you have a positive bias, you turn on the current, right? Because I attract electron, I form the channel for electron to flow. In PMOS, if I have negative bias, I turn on the transistor because I attract the hole, so I have the channel for it to flow. Okay? So we can just go over everything like what we did last time for the NMOS, but we will not do that because this is not a device class, right? But we will try to understand how to determine whether it is in saturation or in linear, right? So I'm going to give you a table. Let's think about this. I have NMOS. This one I know already. When is it cut off? It is when VGS less than VTH. Thank you. And when it is in linear mode, but definitely I need to turn it on, VGS larger than VTH, right? And we just discussed, we also want VGS minus VTH to be larger than VDS. That is linear mode. Okay. Now, if I did not look at the cheat sheet actually, but just like what we just discussed, I know that when linear, VDS needs to be small. That's why I know that it has to be larger. It would be good if you can memorize this with this trick, right? And when it is in saturation, well, definitely it needs to be on, and VGS minus VTH now smaller than VDS. Okay, so that is what we learned last time so far. How about for PMOS? Now you can go through the math yourself. You can have your own way of memorizing. But for me, I memorize in this way. I'm going to say VGS. I'm going to copy the NMOS. But just flip the sign. VGS larger than VTH. Now some of you might want to do VSG smaller than VTH. That is also fine. Okay? But that is the way I memorize it. So, and then for linear, it is the same. I have VGS smaller than VTH. Right? Here I'm just showing you how I memorize it. You can have your own version, right? And then VGS minus VTH needs to be less than VDS. For saturation, it's the same. VGS minus less than VTH, so to make it on. And then for VGS minus VTH, it needs to be less than VDS. Okay, that's how I memorize it. Yeah. Oh, greater, sorry. Thank you. But how you memorize it, how you write in your cheat sheet is one thing. How you use this is another. You need to make sure that what you are doing here, what do you mean by larger or smaller? How do you do the substitution? So let's do an example. This is very important. If you don't know how to do an example, you don't understand this example, then you better make sure. Otherwise, you will mess up many things. Right here, I just remind you, VTH is negative. And VG needs to be less than this is equivalent to this one. Think about this. If I want to turn on VGS less than VTH, do you see that? Yeah, it is the same because VGS equals to VG minus VS, right? So let's look at an example. For example, if I assume the VTH equals negative 1 volt, just assumption, and I have this transistor arrow going in, so I know this is PMOS. And I assume this is at 5 volt. This is at 1 volt, and this is at 2 volt. So I want to find out whether this is in saturation, cut off, or linear. Okay? Where is the source? Is it the one at 5 volts or the one at 1 volt? 5 volt. Because we're talking about PMOS. What is the carrier? It's hole, not electron, right? Hole comes from the higher potential, right? So this is source and this is drain, right? This is the first thing you need to do when someone hand you a circuit. You need to make sure which one is source, which is drain. So from there, I can start doing this. First, what is VGS? VGS is VG minus VS. So what is that? 2 minus 5 equals negative 3 volt. Looks weird, right? Maybe you forgot all this basic thing, but looks weird. But it is the definition. If you want to use this equation or your equation, you need to find out what is VGS first, right? Second, what is VDS? 1 minus 5 equals -4, right? And just to be sure, VTH equals to -1, right? Because we want to compare. So from here, I see VGS compared to VTH, which one is larger? VTH is larger, right? Because VGS is -3. This is -3. VTH is -1. And based on my equation, this is on. Okay? And then, a PMOS? What is?
Isn't that schematic the drawing for PMOS?
It is a drawing for PMOS, yes.
So VGS has to be greater than VTH.
No, to be off, right? Off is greater. Yeah. It's kind of opposite to NMOS. Now, how about VGS minus VTH? What is that? We need to be very careful. -3 minus -1, which is -2. Okay? So -2 compared to VDS -4, it is larger than VDS, right? Because this is -4, right? Because of this, this is at saturation. Now, intuitively, I should be able to see this because I know that I need the gauge to be low in order to turn on. So I compare to 5, I am 3 volts lower than 5. And my VTH is 1 volt, -1. So I'm enough to turn on. And then compared to the drain, if I want to be linear, it's just like that. I need to be 1 volt lower than the drain. But actually, I'm higher than the drain. That's why it is saturation, right? So if I'm in an interview, I will use this. But if I'm nervous, I forgot about this, I will just check this table and do it very carefully. And now it's all up to you. You want to have this intuition, then think about it, practice more. If you just want to check the table, it's still fine. Because checking the table is what you're probably going to do in 10 years later if you are not working in this field, right? But you need to be very rigorous. When I do VGS, I really do 2 minus 5. Do not just guess or just over say, okay, maybe 1, maybe 2 and 1. Don't do that. You know 99% of the chance you are wrong. Unless you're very familiar with this. Same for me. I will be very careful. Okay? Step by step. Okay? Okay. So then we learn PMOS. And we are not going to derive the equation again because everything will be the same. It just will change the polarity, right? So you can come up with the linear mode. The trial here means linear mode, right? This is linear equation and saturation equation. These are the equation that we have. Now, I really don't know why I already fixed this, still like this. But I like to use this one. That is what I use. I still use exactly the same equation I got in NMOS. You see, they are exactly the same. They are exactly the same. Except that I just make to be very careful. I put the absolute value along the VDS, VTH, VGS. Okay? Now, but this one I need to be careful. I need to make sure that they are really in the saturation and trial region before I use this equation. Okay? So otherwise, I just make everything absolute and use the same equation from NMOS. And remember that the current goes from source to drain. right? So you have your own way. Some people, many semesters, people say, oh, it doesn't look like the same as what I learned in E122. Fine, you just use the one that you are familiar with. You will get the same results. You just need to be very careful when you do the substitution. Okay, so that is everything about PMOS. Okay, so we have